All right, rolling.
Are we rolling?
Not us.
Is it running?
Yes.
Oh,
Now.
Now, okay, I've got it filling.
What's the time?
I'm just filling, it's just a
Where's your
warm up
top,
back.
where's your top hat?
Oh,
The cane.
What's the time? What is it, 12?
11:45, isn't it?
11:45. Get this table.
Oh, that's it here in case I just.
Okay, I'm building your network. Just before, are we running? Yeah. Okay. Just before we move into the neural network thing, I just want to do one little explanation of something which might come in helpful later on. I've got a function y equals x squared. And I've got another function that equals y cubed, which of course is x squared cubed, which is x to the sixth. Okay? The details don't matter. Could have used sine function or anything, just a function. Now, we know that dy dx is 2x. If you don't know that, get a year 11 maths book. We know that z to y is 3y squared. So what's z dx? Well, we sort of know cheating, it's going to be 6x to the fifth. But look, the z dx is the z to y dx, what's called the chain rule. The z to y is 3y squared. Y dx is times 2x. And we know that y is x squared, so it's equal to 3 times x squared squared times 2x, which is 6x to the fifth. No prizes there. It's just pretty straightforward. Year 11 maths, probably year 10 nowadays. This chain rule is very important when we're doing backpropagation. Or to be more persistent, correct. Training by backwards propagation of error. Training by backward propagation of error. It's very important in this backwards propagation of error to note that all these functions were differentiable. Okay? I'll give you an example of a function that's not differentiable. We'll have a side function. It's not differentiable at this point and this point. There's just no derivative at that point. Unfortunately, it's the sort of function we'd like to choose for our activation function. So what we do instead, we use a function that looks like this. And we can generate that with a number of things, including tan, THANH, all sorts of things. We can generate a function that sort of resembles a Heaviside function, but is continuously differentiable. Okay, that's just by the way. And one more fact while we're on mathematics. This is a curve which is monotonic. If you're riding a bike, it's all uphill. This is a curve which is not monotonic. Got a bit of a rest there. Now when we do this the other way, when we have an error function, and the value of x, we'll say, if an error function looks like this, we can just keep on going downhill and eventually get this minimum. But if the error function is like this, we might get stuck here, not realising that if only went up a little bit earlier, we had a much lower error somewhere else. So it's really important that error functions are smooth, not and error functions which are like this come from monotonic activation functions. And we'll look at activation functions. I'm sure you've read the stuff I said yesterday, so you know what they are. So it's really important that we go for a global minimum rather than this, which is a local. Some functions give us global minimum, some give us local. Now, proceeding on with our maths, just one more thing that I can think of now that might help. I'm going to take a sort of a contour map. This is high, low, low. Okay, I'll put that in red so you can see. This is high out here. There's a low, there's another low. It looks a bit like a weather map. Now let's say we were looking for a minimum and we started off here. Okay, downhill from there. Downhill takes us to this one here. There you go, got there. Found the minimum. Unfortunately, it's not like global minimum, obviously. We found this thing. If we'd started here, we said, oh, downhill takes us all the way to there. So, one way of avoiding finding local minima is to start at different places on the plane, on the solution space, and then head downhill. If you head downhill by the steepest path you can find, it's the quickest way of getting to the minimum. It's a bit like if you're, let's say you're stuck, you've gone to Falls Creek, you're in a whiteout, you don't know up from down, left from right, you can't see more than that. Hop on your skis and see which way you slide. Okay, I'm sliding, it's got to be downhill. Turn a bit, it's not sliding as fast, sliding very fast here. If you keep sliding the fastest, you'll get to the bottom the fastest. You take the steepest descent, you'll get there the fastest. Now, to jump around the plane or the solution space like this, what we do is we start up here. We start off here, and we see what happens, that'll take us into there. And we start off here, and here, and here, and here. We jump all around the place, have different starting points. And with these different starting points, we're going to do that using what's called a genetic algorithm. So there's two components to this neural network we're going to build. One is this idea of going downhill to get to the bottom of the error function. and the other is jumping all around the solution space to get to a different starting point to go downhill. And then we can make life even better for ourselves if we have a monotonic activation function which ensures differentiability, which ensures we don't get these sort of
Localized.
local minima created by the activation function. Okay, so I'm going to rub that off. So do you want to take a picture? Bear in mind the objective of this session is to build a neural network, not to walk away with yet more notes and things. Cam will do the writing of the code, and we'll just criticise. Okay. I don't think you should have written that down.
Oh.
I think that.
Why not?
It's going to be a long process. It's going to be a
Why
very
not?
long process.
Okay.
Okay, hold on. Okay. Right. We're going to start with a three-layer network. That's an input layer, a middle layer, and an output layer. Traditionally, these things are shown as two-dimensional, but there's no reason why they have to be. They could be one-dimensional. Ours is going to be two-dimensional for the following reason. Our test data is two-dimensional. We're going to take different photos of Tam and see if she's awake, asleep, grumpy, not so grumpy, extremely grumpy, very grumpy, just generally degrees of grumpiness. Okay, so we're going to take two different sorts of data. One has got numbers, deliberately done not very well, as opposed to the perfect weight, which is completely closed. And one is going to contain faces. And here again, I've drawn my excellent drawing skills. Unfortunately born in a large year, but that's that's genetic selection for people with mobile phones. That's the mobile phone. That's what I'm listing out for people saying. So. Now these things, of course, can be, we can get these as a BMP, so it's effectively pixelated. Or just a screenshot. So you're just capturing the pixels. Now, if we take this 8, for example, I'll draw a few more lines. I used to like doing this on the kid, so it gave me some satisfaction, I think, because I was a bit strange. I used to like drawing grids like that. It's a big one, that
I'll
big with
start
millimetre.
colouring book now.
Yes, I
Colour
think
you.
Okay. All right, so let's look at pixel number 3. I'll do that a bit thicker, so you can see it on the camera. One, 2, 3, 4, 5, 6, 7, 8. 3, 8. It's got, now we can either say 0 and 1. Right, thanks for gone. Red's not doing too well today. We can either say it's 0 or 1, or we could say it's something like 72% coverage. Okay? This one clearly is 0. Okay? So we've got our input in a two-dimensional grid, right? And because it does make sense in both cases of the numbers and the faces, that proximity has got some, what shall we say, relevance to detection. instead of linearising this into one long vector, we'll retain it as a two-dimensional structure. So it'll be two indices. So we'll basically have, in that case, a structure that looks like that. Where we, in this field here, we might have, for example, I'll pick this one here, 0.72. This is the input layer. It's solely dependent on our data. Its size is solely dependent on the degree of pixelation of the data. If we had more pixels available, we wouldn't be doing ourselves much of a service by coalescing pixels at this stage. We'll leave that for a later stage. And because we've got a two-dimensional layer, we'll have a two-dimensional middle layer, typically smaller by, like it could be 10%, 10 to 20% of that layer. So if that one's got 1,000 pixels, this might have 200. Okay. Now let's take this. So we'll take this node here, which is actually a little, we'll do it in a second. So we'll take that one there. He actually connects to every node. Every node to every node. So if we had, say, 1,000 here, and we had 200 here, we've got 200K connections.